Welcome everyone. So it's my pleasure to welcome Houman Owhadi. We'll be talking about computational graph completion. Houman, the floor is yours. Thank you.
Thanks, Movidian. Thanks for the introduction. And thanks to the organizers for the invitation. So I will start this talk with a few observations to motivate it. This was live before AutoCAD. And this is live after AutoCAD. Computing square root of 2 is hard if you do it by hand, but simple if you use a pocket calculator. You just do it without thinking about it. Calculating a mortgage amortization schedule is hard if you do it by hand, but simple if you do it with an Excel sheet. Why? Because the complexity of a problem is relative to our ability to decompose it by reasoning through simple concepts, encapsulating and abstracting away its technicalities. And if you automate the resolution of those technicalities, then you're only left with manipulating high-level concepts, and you are therefore free to perform tasks of significantly higher importance and complexity. The automation of calculus is an example of such a transformation. Question: is another level of automation and transformation possible for computational sciences and engineering? Well, the main purpose of this talk is to suggest that this question may have a positive answer. This answer is based on three observations. First, most problems in computational sciences and engineering can be formulated as that of completing a computational graph representing dependencies between functions and variables. Some of these functions and variables of the graph may be unknown, and by completing, I mean recovering the unknown functions and variables of the graph. Second, replacing unknown functions of the graph with Gaussian processes and computing their map estimator given the data provides a simple and interpretable approach to completing such graphs. Third, since this completion process can be reduced to an algorithm, as one solves square root of 2 on a pocket calculator without thinking about it, one could, with the proposed automation, solve a complex CAC problem by drawing a diagram. Now, these three observations lead to a general abstract framework, which I will now cover, and then illustrate through examples. So in this framework, we define a computational graph as a graph where nodes represent variables and edges are directed and represent functions. So the graph itself represents dependencies between functions and variables. For instance, the following graph is interpreted as the identity xj equals to f of xi, and we interpret multiple incoming arrows as a sum. So the following diagram is interpreted as xj being equal to f of xi plus g of xk plus h of xl. We use square nodes to represent primary variables and round nodes to represent variables obtained through the aggregation of other variables. For instance, the following diagram is interpreted as z being equal to the vector obtained by concatenating the variables x and y. And this other diagram is interpreted as the following identities holding true. Note that for this graph, the variables of the graph are the entries of this vector x. So we have 6 variables, and the functions of the graph are the entries of this vector f. So we have four functions. We say that vector x is a sample from the graph if the variables represented by its entries satisfy the functional dependencies represented by the graph. Now, if we are given n samples from the graph with n equals 3 here, then we can see those samples as the rows of a matrix X. So that matrix X has n rows because we have n samples, and the number of columns represent to the number of nodes or variables of the graph. Now, for a given sample S, only a subset of the variables of the graph may be observed or measured. And we indicate which ones by using this other matrix M, whose entry Si is equal to 1 if the variable I is observed or measured in sample S, and 0 if variable I is not measured in sample S. Now, using that particular matrix as an example, the following figure shows the observed variables of the graph in sample 1. So those are these variables. And those are the observed variables in sample 2. And these are the observed variables in sample 3. Now, using Python programming notations, we write x of m for this subset of observed entries of the matrix X. Now consider the following problem, which we call a computational graph completion problem. Assume that some of the functions of the graph are unknown. I will use red arrows to represent unknown functions and black arrows to represent known functions. Then, given the data represented by the observed entries of the matrix X, approximate all the unknown functions and recover the unobserved entries of the matrix X. Observe that this problem combines a regression problem, that is approximating the unknown functions of the graph, with a matrix completion problem, that is completing the matrix X. And our solution will be to replace unknown functions with Gaussian processes and compute their map estimator given the observed entries of the matrix X. Now, to describe this general solution, I will first set notations by considering a simple interpolation problem in which you try to approximate an unknown function f mapping some variable x to some variable y, given the data f of xi equals yi for I going from 1 to n. We will represent this data as a dashed arrow from the variable x to the variable y. Now, if you replace the unknown function f by a centered Gaussian process with kernel k, then its map estimator is its conditional expectation given the data. So you recover Gaussian process interpolation. Now, this interpolant can also be identified as the minimizer of the following optimal recovery problem, which is a variational problem in which the quantity to be minimized is the RKHS norm of the interpolant, given the interpolation constraints. And this interpolant admits the following representative formula, in which I'm writing kxx for the n by n matrix with the following entries, and k dot x for the n vector with the following entries. Now, you have to invert that matrix, and the classical way to avoid issues with its possible singularity, bad condition number, or overfitting is to add a nugget or a multiple of the identity matrix to that matrix kxx. And this is equivalent to relaxing the interpolation constraints by adding a Gaussian variable to the output of the function f. So in that relaxed setting, the variable yi is no longer equal to f of xi, but to the sum of f of xi and wi, where wi is a centered Gaussian variable of variance defined by the nugget sigma squared. And if you add those noise variables, then the previous GP interpolant turns into the following GP regressor, and the previous optimal recovery problem turns into the following one, in which you minimize the sum of the squares of the RKHS norm of the function f and of the random variables wi, given the interpolation constraints wx plus f of x plus w equals y. And if you use the constraint to eliminate the noise variables, then you get the following relaxed unconstrained optimization problem, which is essentially Tikhonov regularization. Now, we will employ a similar strategy to relax functional dependencies imposed by computational graphs. What this means in practice is that we let a subset of the nodes of the graph represent random variables, and we will draw those nodes in blue. What we mean by the node I representing random variable is that we assume that the corresponding entry of the matrix X to be independent centered Gaussian random variables, vectors, or fields with covariance matrices or operators KIs. Okay, now we are ready for the solution of the general computational graph completion problem. The precise description of this solution is technical, but I will illustrate it with several examples. So this solution is to replace the unknown functions of the graph by independent Gaussian processes and compute their map estimator given the observed entries of the matrix X and given the constraints imposed by the graph. This is equivalent to approximating X and the unknown functions with a minimizer of the following variational problem, in which the quantity to be minimized is the sum of the squares of the RKHS norm of the unknown functions and random variables subject to all the constraints imposed by the graph and the observed entries of the matrix X. The optimization variables here are the unknown functions, our candidate Z for the matrix X, and these slack variables Y, which correspond to the output of all the functions of the graph. Note that the variables Z entering in the loss are those associated with nodes representing random variables. The kernel and covariance matrices used to define the loss are assumed to be given a priori, but you could also learn them using empirical bias or some variant of cross-validation, such as kernel flows. The first constraint is defining the variables Y as the output of the functions of the graph. The second and third constraints are imposing the connectivity or structure of the graph. More precisely, the second constraint imposes for all square nodes J of the graph the fact that the variable Zj must be the sum of the variables Y labeled by arrows ending in the node J. The third constraint imposes for all rand nodes J of the graph the fact that the variable Zj is the concatenation of all variables Z labeled by nodes I with an arrow from I to J. And the last constraint is the constraint imposed by the observed data. Now, this is an infinite dimensional optimization problem, but if you minimize the loss with respect to the unknown functions first, then you can identify those unknown functions as a function of the optimization variables Y and Z, which are in turn identified by solving the following reduced optimization problem, which is computationally tractable. Now, all the previous equality constraints can naturally be relaxed through the use of noise variables. And if you use that approach, then the previous optimization problem relaxes to the following form. And this relaxation leads to the introduction of nuggets in the kernel representative formulas, enabling the identification of unknown functions given the variables Z and Y. Now, you can also complete the graph by computing the empirical bias estimation of the underlying GPs instead of their map estimation. This introduces the following log term in the reduced variational problem, and I refer to the following paper for differences between map and empirical bias. But the short story is that map has a lower complexity, whereas empirical bias has better consistency. Now, the proposed framework can naturally be generalized to situations where functions are not just acting on variables, but on linear functionals via duality pairing, and these linear functionals could be masses of Diracs composed with differential operators. So for instance, the following diagram where U is mapping X to U of X and its Laplacian at X must be unpacked to the following one, where X is first mapped to the vector whose entries are Dirac at X and a Dirac at X composed with the Laplacian, and that vector is mapped via duality pairing to the vector whose entries are U of X and delta of U of X. This generalization is relevant to PD applications, which I will cover. Now, as our first application, we are going to turn system identification and digital or surrogate modeling into computational graph completion problems. We will use a nonlinear electric circuit as a simple illustration of this application, but evidently you can make the underlying example as complex as you want. In particular, it could be a full-blown climate system. So our first application concerns the identification of the digital twin or surrogate model of this electric circuit, whose RLC components are assumed to be unknown and nonlinear. We also assume that all the voltages and all the currents in the circuit to be unknown functions of time, so we don't know in particular how the first circuit is being forced. Now, we run the circuit between time 0 and time 10, and at times Ts equals to S over 10 for S going from 0 to 99, we observe or measure a subset of the variables representing the state of the circuit. This figure shows the values of the voltage V1 at times when those values are observed. So we make a total of 7 observations or measurements on V1. Now, given those measurements, consider the problem of approximating all the unknown functions, identifying all the currents and voltages as a function of time, and identifying the RLC parameters as a function of currents and voltages. These figures show the values of the measured variables at time when they are measured. Observe that compared to a traditional regression problem, the data is too scarce to recover any of those functions independently from the others. To recover them, we have to exploit non-dependencies between functions and variables. To describe this, write X for the vector whose entries are the variables representing the state of the system. Observe that these variables are related to each other through non-functional dependencies given by the following equations, which are the Kirchhoff laws for this nonlinear electric circuit. Now, we can represent these functional dependencies between variables as a graph, where nodes represent variables and directed edges represent functions, with unknown functions colored in red and non-functions colored in black. And our solution is to replace unknown functions by GPs and compute their map estimator given the data and dependencies. And these figures show the true and recovered functions using this approach. So the method works surprisingly well given that the data was quite scarce. So this figure has to be compared to this one. Now we'll unpack this completion method, which again is the technical part that can be abstracted away and fully automated. To do so, I will formalize the representation of the data. Remember that we run the circuit between time 0 and at time 10, and at time Ts equals S over 10 for S going from 0 to 99. We observe or measure a subset of the variables of the graph. Now, if for each one of those samples indexed by S, we write XSV for the value of the variable V in sample S, then XSV can be seen as the entry SV of some matrix X that has 100 rows because we have 100 samples and 14 columns because we are tracking 14 variables. Now, for each one of those samples, we only observe a subset of the variables, which means that we only observed a subset of the entries of that matrix X. Those entries are colored in white in the following figure. For instance, in sample 5, we observe T, V1, I1, and L1 of I1 For sample 58, we observe T R of I1 and dV3 over dt. And for sample 70, we observe T, I2, and V3. Now, again, our solution is to replace unknown functions by GPs and compute their map estimator given the data. To describe this, write F for the vector whose entries are the unknown functions to be identified. Write M for the Boolean matrix whose entry SV is equal to 1 if variable V is measured in sample S, and 0 if variable V is not measured in sample S. And using Python notations, write X of M for the entries of the matrix X that are observed or measured. Now, to approximate the unknown functions and complete the matrix X, we minimize the following loss, in which Z is our candidate for the matrix X, and I will now unpack that loss. The square norm of F is the sum of the squares of the RKHS norms of the unknown functions with respect to the following Gaussian kernel. Note that this kernel does not add any prior information on those unknown functions besides regularity. The L1 term in the loss enforces dependencies between unknown functions and variables. For instance, the term highlighted in green enforces the constraint that the variable representing the value of V1 is obtained by mapping the variable representing the value of the variable T via the unknown function V1. The L2 term in the loss enforces dependencies between known functions and variables. So for instance, that term highlighted in green enforces the constraint that the variables representing the values of I1, I2, and I3 must be such that I1 plus I3 minus I2 is equal to 0. And the last term in the loss enforces constraints imposed by the data. Note that the terms L1, L2, and L3 are soft constraints, which can be turned into hard constraints. Now, to minimize the overall loss, we minimize over unknown functions first. And since the problem is quadratic in these unknown functions, we have formulas representing those minimizers as functions of the unknown variable Z. For instance, the overall loss is quadratic in the unknown function V1, and minimizing over V1 given the variable Z is equivalent to solving a kernel ridge regression problem whose minimizer is given by the following formula. And if you do the same for all unknown functions, then you reduce the previous optimization problem to one that depends only on Z. And that one you can minimize with variance of gradient descent or Gauss-Newton. Okay, now as our second application, we're going to formulate the problem of solving and learning nonlinear PDEs as a computational graph completion problem. This formulation is a reinterpretation of the Gaussian process method introduced in this joint work with Yifan Chen, Bamdad Hosseini, and Andrew Stewart. And the point that I want to make here is that once you have drawn the graph, the computational graph representing your PDE, your problem is as good as solved in the sense that the completion part could be automated by a glorified pocket calculator. Now, the underlying method can be applied to arbitrary nonlinear PDEs, but for ease of presentation, I will describe it first for the following nonlinear elliptic PDE, in which f, g, and tau are continuous functions such that this PDE has a unique strong solution. The nonlinearity in this PDE is tau, which we assume to be continuous. And as an example, you can take tau of u to be u cubed. Now, observe that solving this PDE is equivalent to completing the following computational graph. This graph has only one unknown function, which is the solution of the PDE. Now, since this PDE is well posed, you may think that its solution is not unknown, but from a computational perspective, you can only compute with finite information, which means that you can only compute the values of f and g at a finite number of points. Therefore, from an information-based complexity perspective, U is as good as unknown, and the data is obtained by the computations of the values of F and G at a finite number of collocation points in the interior of the domain and on its boundary. Note the data also corresponds to the observation of subsets of the variables of the graph, represented by these dashed arrows. Then the proposed completion approach is to replace the unknown function U by a centered Gaussian process with kernel K defined on the domain omega of the PDE, and approximate the solution of the PDE with its map estimator, the map estimator of that GP, given the identities imposed by the graph at the collocation points. So in that expression, the variables zi1 and zi2 are the values of the intermediate variables of the graph at the collocation point xi. These intermediate variables are unknown, but their nonlinear combination through this known function is known as the value of the right-hand side of the PDE at the collocation point xi. Now, this map estimator can be identified as a minimizer of the following variational problem, where the quantity to be minimized is the RKHS norm of the function U, defined by the kernel K, and the constraints are requiring U to satisfy the constraints imposed by the graph at the collocation points. Therefore, given a kernel K, the proposed approach can be summarized as approximating the solution U dagger of the PDE with a function UN, minimizing the following nonlinear optimal recovery problem, in which the quantity to be minimized is the RKHS norm of the function U defined by the kernel K, and the constraints are requiring U to satisfy the PDE at a finite number of collocation points xi. Note that the PDE constraints at those collocation points depend on whether they are located in the interior of the domain or on its boundary. Then we have the following theorem. Assume that the kernel K is chosen so that its RKHS space is continuously embedded in the subspace HS for some S greater than the dimension of the space over 2 plus the order of the PDE, which is 2 here. We need that condition to ensure that the PDE can be defined pointwise for the elements of that RKHS. Assume that the solution of the PDE belongs to that RKHS, and assume that the field distance between collocation points goes to 0 as the number n of those points goes to infinity. Then as n goes to infinity, the approximation UN identified by our method converges to the solution of the PDE, where the convergence holds pointwise in the domain and in the subspace HT for all t smaller than s. So this theorem is essentially saying that the proposed method is guaranteed to converge as the collocation points become dense in a domain if the kernel K is adapted in the sense that the solution belongs to the RKHS space defined by the kernel K, and that space has enough regularity to be embedded in a subspace containing functions with continuous second-order derivatives. Now, this theorem generalizes to arbitrary nonlinear PDEs, and its general form is described in the following paper. Now, I will present the proof of this theorem, not only because it is simple, but also because it reveals a fundamental mechanism supporting kernel methods. And this proof also generalizes to arbitrary nonlinear PDEs. So first, observe that since U dagger is a solution of the PDE1, and since U dagger belongs to the RKHS space defined by the kernel K, U dagger satisfies the optimization constraints of the variational problem 2. And since UN is a minimizer of 2, we deduce that the RKHS norm of UN is bounded by the RKHS norm of U dagger. Now, since the RKHS space defined by the kernel K is continuously embedded in the subspace HS, we know that the following inequality holds true for all function f. Therefore, we deduce that the HS norm of UN is uniformly in N bounded by a constant C times the RKHS norm of the solution of the PDE. Now, since the subspace HS is compactly embedded in HT for t smaller than s, we deduce that UN converges towards some limit in HT and in situ along some subsequence. Now, since UN satisfies the sequence UN satisfies the PD at collocation points, and since the field distance between those collocation points goes to 0 as n goes to infinity, we deduce that this limit must be the strong solution of the PD. And since this limit is unique, we deduce that the whole sequence is converging. Okay. Now, for the practical implementation of this method, this infinite dimensional variational problem can be reduced to a finite dimensional one by introducing the slack variable z corresponding to the values of u and of its Laplacian at the collocation points, and then minimizing over u before minimizing over z. Note that this slack variable z are the intermediate variables appearing in the computational graph. Now, given those variables z, the minimization over u is a linear optimal recovery problem for which we have the following representer formula, which I will now unpack. So in that formula, z is a vector obtained by concatenating the slack variables z1 and z2, corresponding to the values of u and of its Laplacian at the collocation points. To describe the other terms, I will write phi for the vector whose entries phi I are delta Dirac functions at the collocation point xi, or delta Dirac functions at the collocation point xi composed with the Laplacian. Kx phi is a vector whose entries are obtained by integrating the kernel k supported at the point x against the functions phi I, and k phi is a matrix whose entries are obtained by integrating the kernel k against the functions phi I and phi j. Note that the entries of the vector kx phi and of the matrix k phi are pointwise evaluations of the kernel k and of its Laplacian. So according to this formula, to identify u, we only need to identify the slack variable z, and these variables are identified by plugging this representative formula into the previous optimization problem, which then reduces to the following finite dimensional optimization problem over z. Now, to solve this reduced finite dimensional constraint optimization problem, we use the constraints to eliminate one of the optimization variables, which here is the vector z2, whose entries are the values of the Laplacian of u at the collocation points, and we turn this non-linearly constrained quadratic optimization problem into an unconstrained non-quadratic optimization problem. Now, to solve this unconstrained optimization problem, we use a variant of the Gauss-Newton algorithm. This algorithm is an iterative algorithm obtained by successively linearizing the nonlinearity tau around the previous approximation of the solution, and by solving a quadratic optimization problem to get the next approximation of the solution. In practice, this Gauss-Newton algorithm converges in 2 to 7 steps, 2 steps for that particular nonlinear elliptic PDE, which means that the complexity of our nonlinear PDE solver inherits the complexity of inverting dense kernel matrices. And we are currently adapting the algorithm found in this paper to do so in near linear complexity. The following numerical experiments compare the convergence of the finite difference method with the convergence of the proposed method using a Gaussian kernel. So you get convergence to machine precision. Now, as mentioned before, this method and its convergence theorem generalized to arbitrary nonlinear PDEs. And as an example, these figures illustrate the accuracy of the method for Berger's equation when using the following anisotropic kernel, in which the length scale of space has been chosen to be smaller than the length scale for time to capture the underlying shock. These figures and this table show the accuracy of the method for Eikonal's equation with a Gaussian kernel. So here a Gauss-Newton algorithm converges in six steps. Now, this method can naturally be extended to inverse problems. And as an example, consider the problem of approximating the unknown solution u and unknown coefficient a of the following elliptic PDE, given f and g and given the values of U at a finite number of measurement points, which are colored in pink in this figure. Then the proposed approach can be formulated as completing the following computational graph, where U and A are the unknown functions of the graph, and the known functions are enforcing the structure of the PDE. Here, the data is obtained by the measurements of the value of U at the pink collocation points, the measurements of the right-hand side F at the blue collocation points, and the boundary value G at the orange collocation points. The GP completion is then equivalent to recovering the solution and the coefficient A of the PDE by minimizing the sum of the squares of the RKHS norms with respect to two possibly different kernels, subject to the PDE being satisfied at a finite number of collocation points on its boundary and in the interior, and also subject to a measurement of the values of the solution at the data measurement points. And as mentioned before, for the practical implementation of this method, you need to introduce the intermediate variable Z of the graph as slack optimization variables in the variational formulation of the map estimation of U and A. And these figures show the true and recovered solution of the PDE and the true and recovered conductivity coefficient of the PDE. And here the Gauss-Newton algorithm converges in 5 steps. Note that we are solving both the forward and inverse problems at the same time, whereas the classical MCMC approach is to iterate between solving the PDE and solving the inverse problem. Furthermore, again, the complexity of the method inherits that of inverting dense kernel matrices. Okay, so this was an application to solving and learning PDEs. Other applications include climate/weather modeling and forecasting, learning stochastic dynamical systems, learning Hamiltonian systems, dimension reduction, etc. The underlying principle behind those applications is always the same. Draw the graph, replace unknown functions by GPs, and compute their map or empirical bias estimator to complete the graph. Since artificial neural networks can be seen as a particular instance of computational graphs, you can also use the proposed approach to analyze and generalize them. I will now illustrate this point for ResNets in the setting of the following supervised learning problem.
So there is someone who has a question, actually.
Yeah, go ahead.
Yeah, so you want to unmute yourself, Gian?
Yes.
Yeah.
Okay. So usually nonlinear PDE have non-unique solutions. So when here you notice that you add a viscosity term, then that's a viscosity term will essentially control the accuracy of your approximation. So how those how accurate the results can be
Very good
by
question.
using such kind of framework.
It depends on the underlying kernel. So note that the assumption of convergence in the theorem is the assumption that the solution of the PDE belongs to the RKHS space defined by the kernel, right? So if the solution of the PDE is singular, and if you use a smooth kernel, then that assumption is violated, right? So you don't have guaranteed convergence, and you're going to lose accuracy. Now, in practice, the fact that the accuracy of the method depends on the underlying kernel, you can also understand it as the accuracy of any numerical approximation method, depending on the underlying choice of basis functions if you are using a finite element method. Now, if the solution of the PDE starts developing a singularity, then the solution may be irregular with respect to a smooth kernel, but regular with respect to a kernel that is informed about that regularity, right? So the notion of regularity is really relative to the choice of kernel that you pick. So if you know that your PDE is developing a shock or something like this, and if you use a kernel that can handle the shock, then you will have convergence and you will have good accuracy. If your kernel that cannot handle the shock, then you will lose accuracy.
I see. So now that you also use the ferrocotissar inverse problem.
Yes.
You have interior data, interior observation. In many applications, we usually only have boundary measurements. So
Yes.
how the kind of framework can be used for those kind of setup?
The exact same way. It works the exact same way. So this is just a very simple toy example. The points, the pink points at which you measure the value of the solution do not need to be interior. They could also be on the boundary of the domain. Right. So if you are interested in electric impedance tomography, for instance, what you will end up measuring will be the directly boundary condition at a finite number of points in the boundary. The directly Neumann condition.
Okay, thanks.
You're welcome. Okay, so now I'm going to illustrate an application of this framework to neural networks in the setting of the following supervised learning problem, in which you seek to approximate an unknown function f dagger, given some input-output training data on that function. Then the ResNet solution to that problem is to approximate f dagger by completing the following computational graph, corresponding to the composition of some function f with a deformation of the input space VL, obtained as the composition of L functions, each one written as the sum of the identity map with a displacement VI. Then the deep learning approach to completing this graph is to replace the unknown functions f and VIs by 1 or 2 layers neural networks, and then minimize the data mismatch with respect to the parameters of those networks. Now, instead of using the deep learning completion approach, you can use the GP completion approach. For this graph, this approach can be summarized as replacing the unknown functions f and vi by independent GPs and computing their map estimator given the data, which here is assumed to be noisy. Now, this is equivalent to recovering those unknown functions by minimizing the following loss, in which these are RKHS norms defined by two possibly distinct operator or matrix valued kernels K and gamma. Furthermore, if you choose those kernels to be the following ones, then you recover ResNets with L2 regularization on weights and biases as a particular case. Now we have the following theorem for the general case. As the det L of the network goes to infinity, the adherence values of the regressor obtained by minimizing the previous loss are of the form f composed with phi1, where phi t is the flow map of the vector field v, t is a continuous parameter indexing the depth of the limit network, and v and f are identified by minimizing the following continuous loss. Note that this continuous loss looks like the type of loss functions used in image registration to identify the best alignment between two images based on landmarks placed on those images. But here the images are replaced by abstract and unexpressed functions, and the landmarks are replaced by our training data. Furthermore, we have the following representative formula for minimizers of this continuous loss. To describe this, we write Q of t for the image of the input data x under the flow of the continuous graph at that t. So these QTs are essentially the intermediate and unknown variables appearing in the continuous graph. Then the following formula represents a minimizer V of the continuous loss as a function of the kernel gamma appearing in the loss, and the trajectory defined by Qt corresponding to the deformation of the input data as it propagates through the continuous layers of the network. Now, if you take that formula and you plug it back into your continuous loss, you get that the trajectory defined by Qt must satisfy the following list action principle. Now, since we have a list action principle, we deduce that if we introduce the following momentum variable P, then the pair QP must be a solution of the following Hamiltonian system, which provides a constructive proof of the ODE interpretation for ResNets with train weights and biases. Now, so far we have looked at computational graph completion problems where the structure of the graph was given a priori. Question: can you use the data not only to complete the graph, but also to learn the structure of the graph itself? Well, I will now illustrate a positive answer to this question by considering the following empirical mode decomposition problem as formulated by Huang. In this problem, you observe a signal V on the time interval 0, 1, and you try to recover the modes composing this signal. What we call modes are quasi-trigonometric functions of this form. You don't know how many modes are composing your signal, and the only thing that you know about each mode is that it is a quasi-trigonometric function with an unknown slowly varying amplitude and an unknown slowly varying frequency. Now, we are going to solve this problem by learning the structure of the underlying computational graph from the observed signal itself. Our first step is to decompose the signal V over finer modes living in the linear span of Gabor wavelets, which are essentially windowed trigonometric functions characterized by a time tau and a frequency omega. This can be summarized as completing the following computational graph, in which the unknown functions are those fine modes indexed by a time tau and a frequency omega. Now, to complete the graph, we identify the kernel of each fine mode by replacing the unknown functions, replacing the unknown coefficients in front of the Gabor wavelets by white noise, and then computing the covariance function of the resulting GP, indexed by the same time and the same frequency, and serving as a randomized surrogate for the underlying fine mode. Then you can approximate the fine mode VT omega by computing the conditional expectation of the GP xc to omega, given that their sum must be the observed signal V. Now, our second step is to quantify how much each fine mode contributes to the overall decomposition of the signal. This contribution or activation energy of each fine mode is quantified as its inner product with the overall signal, where the inner product is the one associated with the kernel K, defined as the sum of the kernels of the fine modes. This is what this activation energy looks like as a function of time and frequency, and it essentially reveals the presence of 3 coarse modes in the signal, and these are the modes that we are trying to recover. From the GP perspective, this activation energy quantifies how much each fine mode GP has been activated by computing its conditional inner product with the signal V. This conditional inner product is also equal to the variance of the inner product of the fine mode GP and the signal V, and the sum of these variances is equal to the RKHS norm of the signal V. So you can think of this decomposition as a variance or RKHS norm decomposition, and this kind of decomposition is a very useful but little known property of additive kernels. Now, in our third step, these coarse modes are identified by using the GP activation energy to update the computational graph. The new elements in this graph, is the aggregation of the fine modes into 3 separate coarse modes. To perform this aggregation, we use this activation energy to partition the time frequency domain into 3 subsets, A1, A2, A3, and recover the coarse mode I as the sum of the fine modes indexed by a time and a frequency in AI. And these figures show the true and recovered modes, so the method has near machine precision accuracy. And I refer to this book for further refinements of this approach to situations where the underlying waveforms are also known and non-trigonometric.